Okay, we've taken all this moisture we've been looking at last week, and we're finally going to put it into clouds and precipitation. Uh, Something that most of us are pretty interested in. We want to know when it's going to be cloudy outside, or not having sunshine, or when we're going to have the rain, or even snow. We want to know what type of precipitation, and many of us want to know the exact minute it's going to start so we can do other things. So let's look at some of this and see how this all works. So how do clouds and precipitation form? Well, you think you got it down and it's going to be easy, right? No. So water vapor is invisible. So when you see it, it's condensation. It has formed little tiny droplets. And with that, did you know that about 67% of the Earth has clouds almost all the time? And there is something called cloud condensation nuclei. Cloud condensation nuclei can come from volcano eruptions, wind pushing up some of the soil or dirt, forest fires, sea spray, even chimneys. So what are we talking about? Why do we even talk about that? Well, you look at the size of a raindrop here, and this is relatively to each other. Look at how small a cloud droplet is. When a cloud droplet first forms, it is tiny. And because it's tiny, it behaves differently than a lake. It has a very tiny curved surface, and that curve is pretty sharp. But because of that curve, it allows a lot of water to leave that water droplet a lot easier than it would over a lake or a flat surface. So something's got to hold that water in. Otherwise, we actually leave relative humidities over 300% to form these cloud droplets. Obviously, that doesn't occur in the atmosphere, so something else must be causing this to occur. So that's where these nuclei come in. They actually bond with the water at that very small level and create a solution that actually tends to hold the water in place, keeps it being liquid. So these cloud condensation nuclei are needed. They keep the relative humidity 100% or less to form clouds. And as the droplet size then increases, that amount of cloud condensation nuclei in it is going to decrease, but the cloud, by that time, the radius has gotten bigger, so we wind up being able to keep these clouds and raindrops. There's another problem. Ice doesn't freeze. Ice. Water droplets do not freeze at 32 degrees when they're up in the cloud. Why is that? Well, again, they're circular. They have this kinetic energy in this little tiny circle that keeps them from freezing. They just don't freeze. And they won't until you reach the Schaefer point, which is around minus 32 degrees Celsius. So that is really cold. So why do we have ice and clouds? Why do we have snow at the ground in the wintertime at 32 degrees or even above? Because we have ice forming crystals. And guess what? They're not exactly the same, but they have a lot of the same characteristics as cloud condensation nuclei. So with that, when these get into a cloud, they begin to allow it to freeze, usually around minus 10 degrees Celsius or 16 degrees Fahrenheit. So we have a lot of supercooled water in clouds. So once these ice crystals begin to form, then they begin to take over and become the dominant part. So within that very small kinetic energy range there, once they begin to grow again, they become ice crystals. You begin to get ice crystals are frozen, they have a little bit less kinetic energy. So why doesn't all these cloud droplets fall down to Earth? Well, you would think they would. Gravity's pulling them that way, right? But air is probably rising. That's one thing against it. friction's probably occurring. Oh yeah, that's another thing against it. So that it really holds up this clouds, keeps them in the air, suspended, until they get these precipitation particles get big enough to begin to move to the ground. And once they get big enough, then they begin to go down there and they'll reach a steady state, or velocity that is always going to be the same because friction is pushing it back up, gravity is pulling it back down at the same rate. So they reach a point that this is the exact speed they're going to hit, and they never go greater than that. So how do we form precipitation in clouds? We've talked about now the clouds getting formed. Well, the easiest process is called collision coalescence. It occurs in warm clouds. What do we mean? Well, that's temperatures that are greater than freezing, and there is no ice in that cloud. So you look at that, and guess what? A lot of Ian probably did not have ice in the cloud. So where there was no ice, this process dominates. Typically dominates in the tropics, and it dominates when there's a lot of moisture in clouds that are warm. The warmer clouds, the more moisture they can hold. So like when I had my rain yesterday and did it last night and got my 3 inches or more of rain, a lot of the processes probably were going on in collision coalescence that was forming my raindrops. What happens? One raindrop slowly starts falling, a little tiny drop. It hits other cloud droplets, and begins to pull them in. As you can see here, they get bigger and bigger until finally they're big enough that they can fall down to the ground. So the more moisture in the clouds, the more droplets are in the clouds, the quicker, the easier this process will work to bring rain to the ground. But almost all precipitation starts out as snow because the upper part of the atmosphere is very cold. Now here's the Bergeron-Findyson effect. This is a little different. So let's take a look at it. Here you have a few ice crystals have begun to form in the cloud from the ice crystal nuclei getting in the cloud. Well, vapor pressure over ice is lower. Saturation vapor pressure is lower. We saw that last week. So what does that mean? Well, that means the vapor pressure is higher over these little raindrops, cloud drops that's here. So higher pressure is going to move to lower pressure. You wind up with more and more of these snowflakes growing and taking over. And eventually they dominate. It becomes all snow. And the snowflakes have grown. So what they're doing is they're big enough now to fall. So the precipitation that literally begins in that cloud begins as snow. Sometimes this rain and snow evaporates on its way down to the ground, and that's where you see the virga. Other times, it just comes on down and we get rain or snow. Rain is basically, 0.5 to 6 millimeters. Big drops. They're flattened out as they come down. They're not tear-shaped. And drizzle is very tiny. Raindrops, literally. Usually come out of very low clouds, and mostly limited in collision coalescence. Ice, snow. Guess what? It has all different shapes. If I was to tell you that you were going to have this thin plate shape at your house from this event coming up on snow, but the reality occurred that you had the dendrites. Look at the difference in size. Same amount of moisture, same amount of precipitation fell. Which one do you think would give you more snow? Well, the reality is dendrites give you the most snowfall. They're significantly larger than the other types of snow things that you can see here. So what happens when you're forecasting the amount of snow at your house? If I'm a forecaster, I've got to determine which one of these types is most likely to be occurring at your house. Where is most of this precipitation developing? What temperatures and what type of precip? Will it be dendrites or will it be another form? That can make the difference between maybe getting 3 to 5 inches and more likely 6 to 9 inches. Which one's going to cause you more trouble driving? Now here is what typically happens as the precipitation is coming out of the cloud. It starts out as snow when the birds are on fin dicing. And many times we have learned temperatures change in the upper atmosphere. Maybe there's a section that is warmer. Warm air aloft. I had that yesterday coming in. So warm air aloft, what it does, temperature gets above freezing. Maybe not for a big layer. But when it does, it doesn't take a lot to melt that snow, to turn it into water. And then if you have a large layer below that, that's below freezing, you're probably going to get sleet. Now, if you have only a small layer, well, maybe you're only going to get freezing rain. And at most times, though, most of the precip we get is rain. So generally the temperature stays above freezing all the way down to the ground. So you can see how temperatures aloft influence what type of precipitation you're going to get. Another part that has to be forecasted to determine your precipitation type. Here you can see the freezing rain or freezing drizzle at the ground. Radar. It's a great way to determine what's going on in the atmosphere. Basically a big microwave, except it listens. There are microwave pulses sent out. And when they're sent out, that big antenna up there is listening. So it sends a burst out, and it listens about almost 100 times longer than the amount of time it took to send out that energy. So very tiny amounts of energy are actually going out. Actually, it's less than what actually goes out from where you stood next to a microwave oven that was shielded from you. The energy coming out of a radar is less than that made it through that microwave shield. So it's not very much. But through that, it reflects back and we can see precipitation. And other things as well. Sometimes we see bugs. Sometimes we actually see birds taking off. I have watched huge areas of birds fly out from a lake. You can see it in the morning where they had nested all night, took off in the morning, and there's this big echo forming over the lake because these geese were flying out. Then we get velocity mode. What does that do? That detects the speed of these particles. Here you can see a radar. And here you can see the Doppler effect. By knowing the Doppler effect, I can calculate how fast a particle is moving toward or away from the radar. So with that, I have the reflectivity here. I can see all this rain coming down. Heavier precip gets me a better return because there's more precip. Bigger drops and all send back more rainfall to me. And then the radar. And here's a tornado debris signature. When you look at the Doppler radar here, you can see winds actually changing direction very quickly, right around one little tiny area right here. That circulation and very strong winds actually detects a tornado. Here you can see a tropical storm hurricane coming ashore in the Carolinas. There's another system being tested, phased array radar. It's used by the military in ships, but it's an extremely expensive radar. And while I had the privilege of working on it out in Norman, Oklahoma, it's not going to be out into the field where you're getting it at your house or using it for many, many years in the future. Also, radar can estimate the amount of rainfall falling. Final part of this chapter, we talked about clouds, cirriform, stratiform clouds, warming cloud cops, and how they're composed here. Here are some cloud streaks over the water, lakes, and fog. Fog actually can form on the oceans or lake and advect in. I had this happen when I was at Florida State. Fog came in one time off of the Gulf of Mexico. I was watching a football game, and you could just gradually watch the winds pull that moisture in off the Gulf of Mexico. And by the time halftime came, you couldn't see across the field. So with that, let's just take a quick peek at a couple things on radar. This is today's radar. So I wanted to try to get an idea. When it comes back up here, here we go. This is the total rainfall. And we are looking at dual pole radar. Dual pole radar is a little bit different. It adds another dimension, but it gives more accurate. You notice there are some pretty high precipitation values right in here. Maybe upwards of 2 to almost 3 inches right in this area. A lot less otherwise, some bigger amounts here. So this is storm total precipitation. It's one of the products we get. Or we could look at reflectivity, which would be the current rainfall, and you can see it here between Charleston and Beckley, basically. Nice rainfall there. So let's take a look at what dual pole is. I wanted to really make sure you understand this because it's a question in critical thinking on dual pole radar. So normal radar, not dual pole, transmits a horizontal pulse out. However, dual pole transmits a horizontal and vertical pulse. So it gives me a shape of what it's hitting. It means I can distinguish maybe between birds, maybe between debris, or between sizes of raindrops. But one of the coolest things I think about dual pole radar, I can see hail. We could infer hail because of strong return. But now we can look at the change in shape over a short distance. And hail really changes, is a lot different shape than water droplets. And here around it are all these water droplets not changing shape that much. And right here, very fast changing shape. We can actually say, oh, right in this little area, here's probably the biggest hail. Great for forecasting and giving you all a warning. So I hope you got something out of this, and please don't hesitate to ask if you have any questions.